All right. Welcome everyone to our Rust Munich Meetup edition, the first of this year, 2024. And speaker Heiko got a sickness and he cannot have his talk today. So it's suspended. It would be about distributed tracing. Maybe we can have it next time. And yeah, my apologies on the short notice.
We would have waited.
Yeah, it is probably really good. I had him. I watched his talk about event sourcing on the Rust Nation UK. It was also really good. And he's a nice guy, by the way. So yeah, today then we will start with our second talk, which is the heat camp project from Kevin. And I hope that everything goes well because my browser died already twice. I hope this doesn't appear again. And I have to excuse the audio because it's coming out of this notebook. I still hope that you can hear him well enough. All right, then. Here is Kevin.
Hello.
And I will put you on main screen. So Kevin, the stage is yours. Have a good talk, and we talk afterwards.
Thanks. So yeah, hello. I'm Kevin, and I'll be presenting you thermal imaging using embedded Rust. Today, unfortunately, I couldn't come personally because I did not have time, but it should be all right. I also won't be talking for very long, but I guess you'll enjoy it. So to begin, I have made a project for the last couple months, and it's about 3D printing. So it includes 3D printing, but of course also Rust. And I'll be showing you. So first of all, why did I do this? It's a self-built project for hobbyists, so everybody can build one for themselves. It's also open source. And yeah, if you have a 3D printer at home or just access to one, you can build one yourself. Also, thermal imaging at home is pretty useful. And for like special things, like taking a look how good windows can isolate the heat from the inside. And it's not that expensive. So it's a good alternative to just buying a regular heat cam. And it's open source, both software and hardware. So you can also modify it to your need, if you want to, of course. So we'll start with the software. A core part of this whole project is a module called RPMLX 90640, and it handles all the communication between the infrared sensor and the Raspberry Pi. So to give you an introduction how this works, we have a Raspberry Pi which contains all the programs. It runs on Linux and connected via I2C. There is connected a sensor called MLX 90640, and this one scans the environment for the infrared rays, so we can calculate the temperatures. Later I'll go on further detail on how it's built. So what the module can also do is color the image, which is like a nice extra feature. But the most important part is that it can actually calculate the image, the temperatures in the image. So I'll show you the rough structure of it. We have the main module, and then there's the board support package, MLX. and this one handles the raw I2C communication between the sensor and the Raspberry Pi, but it doesn't really calculate anything. It just receives the raw data. So then there's a submodule called an MLX EEPROM. This one receives all the raw data, and it then goes ahead and calculates all the temperatures and returns it to the main part. So now we have a grid of temperatures, or more like an array of temperatures, but it represents a grid. And to visualize it, there's another submodule called MLX image. This one takes the temperature grid and colors the image and returns the image that's ready to be drawn to the screen. And this module, it was first developed just for the project, but later I have converted it to be an external part, so I can publish it, and you can reuse this, create in other project the environment, or also get color data. So you don't have to build the camera. You can do whatever you want with this crate. It's open source. It doesn't contain the graphics part. This one is external, but it's also published elsewhere. And in graphics mode, this whole process runs asynchronously in the background. So it just constantly goes in a cycle, reading, and displaying the image if it's ready. So yeah, now we get to how to build the camera. And here's all the stuff you need for building it. So you can see the 3D printed parts in orange and the electrical components in the middle. In the center, we have the Raspberry Pi, and below is the MLX. And here above is the display. And they are all on supports that will later go into the case. So you first connect it up, just like that. And you can see it already works in this state. And but before it starts working, you need to configure the Raspberry Pi, of course. And I've prepared some scripts that go onto the Raspberry Pi and install all the necessary dependencies and such, and also install the program. So after it's done, it usually takes like 20 minutes or so. After it's done, it will restart and display the image. And if it works, if no cables are if we forgot no cables, then we can put it in the case, and then check again if it works. In this case, yeah, it does. So then we can put the lid on and use it. So here in this image, you can see the rough UI. On the left, we have the like preview for the coloring, and you can also see the maximum temperature and the minimum temperature. The center is the image, and on the right are the controls. So if you have noticed already, on the right you can see exposed USB ports, and therefore if you want to take an image, you can insert a USB stick inside, and the USB will be mounted automatically, and via the button you can see here, Save Image, you can then save the pixels, the image. And then there's also the options menu, so you can configure a few things if you'd like. You can see the color mode. I I have implemented 3 by myself, but you can add your own if you want. So first of all, grayscale should be pretty self-explanatory. The hotter something is, the whiter it gets. And of course, the coldest part will be colored black. And then there's what I call cheap, because it looks a bit odd, but the working principle is it interpolates between red, green, and blue, with red being the hottest. Then hue is similar, but it looks more natural. It scrolls around the hue wheel, with red being the hottest and blue being the coldest. And this is like the standard what you use in thermal imaging. Then here the refresh rate. You can increase or decrease it. And this will directly write some bits to the MLX to tell it what refresh rate it should use. And yeah, that's pretty practical. If you use lower refresh rates, then the image will get more blurry, but also more accurate. And a higher frame rate will be less blurry, but it will contain more noise. And finally, we have the layout. Currently it's in right-hand mode, but you can also put it into left-hand mode. Then the entire thing will be flipped. If you're left-handed, it's pretty practical. So, and what I forgot to tell, here you can see there's like a little hole for the stylus. It comes with the display. You can put it inside the case for convenience. So yeah, that's it. It wasn't very long, but the whole project is open source. Both the CAD files and the source code are all published under GitHub. Here's the link. The QR code leads directly to this link. And there's a build guide on there that will go into further detail than I did right now. And externally, the Raspberry Pi MLX module is also published on crates.io if you want to use it. So that's it. Do you have any questions? But I don't know if I can hear you. So how do you want to do it?
So now you should be able to hear us, I guess.
Yes.
Oh, cool.
So depends. So there are questions here. Or first of all, thank you, Kevin, for the talk.
Thank you.
Thanks. Thanks.
So yeah, go ahead with the question.
I hope you can understand it. What is
It's a bit quiet, so but I should be able to.
And I can rephrase it then. Yeah.
So what was the motivation to solve this problem with Rust and not with any other language?
Okay, so the question was, what was your motivation to solve it with Rust and not with any other thing out there?
So first of all, the main features that like are always set for Rust is like the memory safety, because it's a pretty complex application for a single person to do. So the stuff with memory safety and such is really a really good thing to have. I also used the eFrame crate for the graphics of it. And here, of course, you do not have this crate in other languages. And I quite liked it, so that was the motivation. It was also a good learning experience, also a good thing with 3D printing. I learned a lot.
All right.
Thank you.
Thank you. Anyone else? Yeah.
Thanks for the talk. I'm curious why you chose the Raspberry Pi as your main computer.
So the question was, why did you choose the Raspi for your project and not any other device?
So it was out of few reasons for convenience, because we have a graphics interface and the display, it connects to the Raspberry Pi, and there are some drivers online which will handle all the communication between the display and the Raspi, but they only work if there's a whole operating system installed. And here the Raspberry Pi is the best candidate if you want a full-on operating system with Window Manager. And yeah, it also runs Linux, and it's also convenient for USB mounting.
Thank you. Get another one.
It looked like your program communicates with the camera chip, right? The
Yes.
Camera. So was there there's basically crate that talks to that chipset, but you did not have to put any code to run on the camera chip, right? So
Yeah.
you were able, all those crates can use the standard lab of Rust, right? So
Yes.
it was okay.
So from the architecture, we can imagine it as a standalone binary, right? That runs on the Raspi, that leverages the Linux kernel and the drivers in there, that then like sends the commands through I/O pins or whatever to the chip, right? So it's not an embedded use case of Rust,
Yes.
right? So this was the question.
Exactly.
Yeah.
And may I ask one more? So what was your main challenge when implementing this like Rust binary that talks to the camera and then exposes the data to the higher level? Like, I don't know what you use to present them. So what's like then the display X server or whatever that runs there? So what was your main challenge there?
So the main challenge was the configuration. It doesn't have much to do with Rust, unfortunately. It was, as I said, I did not do the drivers myself. I downloaded them online, and I also created a script that automatically installs all of the dependencies and all the packages that are needed. And what I did is for the configuration, we have a just base Linux that starts off on the Raspberry without Window Manager or anything. And the Window Manager is later installed via script. And I kind of had to go through a trial and error there to see what packages are needed, which ones can be omitted. And well, at the end, it did work, which was good. But also like calibration of the display was kind of finicky, because I had to edit the configuration files via script, and that was also like a process of trial and error and seeing like how do I have to do this. For example, at the beginning the touch screen was like inverted or something, so if you were to press on the bottom right, the pointer would actually go on to the top left or something, and I had to figure out how to flip it.
Yeah. Understand. Mario, go ahead.
Did you calibrate the camera, or does it give you correct readouts, physically correct readouts?
So the camera, it comes with calibration data from the factory, so I did not have to determine any values by myself, but the program has to read in all of the calibration data. And if I go back with the slides real quick, I can explain you this a little better. here, this MLX EEPROM, this takes care of all the calibration and all the like complicated calculations that go in with converting raw data to temperatures, because unfortunately we don't get the correct temperatures from the raw information. We have to do a lot of stuff to it before it becomes correct. But luckily, all the formulas which are needed, they are all listed on the datasheet of this MLX camera. So I did not have to like implement this myself. I just had to translate it into Rust. And I did it in like a day, but now it's complete and it works.
Do I have one more?
Go ahead.
What is the minimum and maximum temperature, and what is the precision that you can get?
So it's written in the datasheet with more precise detail than I can tell from memory now, but it does have a great range. So room temperature, temperatures around room temperature are pretty accurate. But if you go like to 100 degrees or 200, it gets less accurate. And I would now say around like 300 degrees Celsius are like maximum if you want accurate readings, or like in the cold range, like -20, -50 degrees before it would not be accurate anymore. But it varies like how much it deviates from the room temperature.
Thank you. I have also one more question. Did you use the image crate, or did you do all the image like math, so to say, by hand, by yourself?
So like, what do you mean precisely? Like displaying the image or calculating the image?
You're also like representing it in memory, and then when it comes to maybe storing on disk, then you have to choose probably a format like PNG or BMP, whatever. So all this kind of stuff. There's this image RS crate, which has also like the encoders for JPEG, PNG, and all that stuff for reading and writing. And certain aspects of compression, of course, and so on. So did you use it, or not at all?
So for saving it, probably yes. I can't really recall adding it to the dependencies. Perhaps it's like a sub-dependency of another dependency, but I did use an external library for converting it to PNG or something. But for example, converting the temperatures, the raw temperatures, which are stored in float, by the way, converting them to colors, this I did myself.
Okay, cool. Thank you. There's one more.
What is the maximum frame rate and how many vectors were you taking?
How many vectors? Or
Array size. What would be the array size?
okay, so the question was, what is the maximum frame rate that you can have, and how much or how many vectors you will get there?
So the maximum frame rate that is possible with the sensor is 64 frames per second. But unfortunately, the display cannot update this quickly, and I would guess it's around 10 FPS, which you would see on the display. And if you have that many FPS, the image gets really noisy. Like I tested it, and if I put my hand in front of the camera, I could almost not recognize it. So it probably has like plus minus 10 degrees of accuracy in the highest frame rates. So I would not recommend using very high frame rates if you don't scan very hot objects.
Interesting.
What would be the resolution? What's the resolution? Highest resolution?
The highest resolution.
We need
Yeah.
resolution.
So the next question was about the resolution that you can expect.
So the resolution, I did not know. I did not write it. Unfortunately, I can't say from memory the exact numbers, but it's like around 20 to 30 pixels. It's not a lot, but that's what the camera sensor has. Unfortunately, we cannot upscale it on the Raspi. So yeah, it's around 20 to 30 pixels. I can go back here. So you can see it's quite pixely, but that's the sensor that I'm using.
I'm wondering, do you think it is possible to use multiple of those sensors as an like array and like increase the resolution by doing so?
Perhaps it would be possible, but it doesn't make that much sense in my brain. If I think about it, maybe if you do like if you position them really precisely next to each other, maybe it would work. But it's kind of it feels a bit like cheating, to be honest, if you put multiple cameras next to each other, because it also has a physical size. You can't put them too close to each other, and you also have to make sure that their frame rates are synchronized. And the thing is, the sensor operates by on its own clock. I think. I hope I'm not saying wrong things right now, but I think it's operating on its own clock, and it always sets a specific flag in its flash, not flash, in its own RAM memory, whenever the new image has been written to the RAM, so it can be sent over to the Raspi for further processing. So it would be pretty difficult. I would recommend getting a different camera if you want higher resolutions.
All right. Yeah, thank you. All right, there's one more.
I think we have time, right?
Sure, yeah, absolutely.
Okay. How is the camera connected to the USB, or which kind of connection?
So you mean the physical connector?
Yeah.
So yeah, the question was how the camera is connected to the Raspi.
The camera, it's connected via jumper wires. Like here you can see it's kind of in the background, but the camera is behind this part here. And it looks like a bit of a mess, but it uses I2C. So there's 4 cables going to the camera, 2 for power and 2 for communication. If you're familiar with I2C, then you probably already know what I mean. But yeah, you can also solder them if you want, but that's kind of a hassle for me. So I use jumper wires. It also allows for quick disassembly if I need to do something. So yeah, it's connected via jumper wires and I2C.
And was there already a kernel driver for I2C available for Raspi? I guess so, right?
So the question was if there was already a kernel driver available for I2C.
So yeah, you have to like enable it on the Raspberry Pi before you can use it. The installation scripts do that automatically. You don't have to do this by hand. But yeah, I had to enable the kernel modules, and I'm also using an external crate for like the system calls, so I can have functions in my code that just do the reads and writes.
Yeah.
Thank you.
Right. Yeah, I think there are no further questions. Then thank you again, Kevin, for this nice talk and presentation. And yeah, give a round of applause.
Thanks.
Good. So I think we will now like go in a little break. Maybe grab one more drink or so and eat something. and then hopefully we will be back with Bernhard. He wants to give a little quick talk about graphs in Rust. So let's see if that works out and when. All right, so stay tuned, guys, and Kevin, you can also stay, of course. But if not, then have a great evening and thanks for
Thanks.
coming.
Thanks, you too.
Hello, everyone. So today we don't have another talk. So Bernhard was not convincible to give us a talk. So we are at the end on our Rust Munich meetup number 1 this year. But I would like to thank Maria that made this possible here. Thank you very much. So she was responsible for organizing it and having her colleagues at SAIS convinced to host us. So it was a pleasure. Thank you very much.
Awesome. Thank you.
All right, guys. Also, I would like to announce the next meetup date. It will be July, probably the 29th or 30th week of the year. So stay tuned on meetup.com. We will announce it pretty soon, and then you can join. All right. Thank you very much, and have a great evening. Bye-bye.